Okay, so today's the last talk. Thanks to everybody who made it to the end. And thanks again to Emma and Christian for helping me organize this. It's been a lot of fun. So as I usually do, I'm just going to remind you guys what happened last week. So we proved last week the slice theorem, which is kind of the heart of the whole paper, both technically and in terms of what actually goes into the solution. And this basically describes the associated graded of the slice filtration on these norms of BPR and norms of MUR. So this we also saw was the same as some kind of equivariant iadic filtration of BPG. And anyway, the slice theorem says that the associated graded is the sort of free G polynomial thing over this Z underline Mackey functor. Okay, and just to... This is just for G cyclic 2 group. And this notation, just to remind everybody, means it's the norm from C2. Yeah. Okay, so, and just to briefly recall the kind of slogan of the proof. It's very sort of technical diagram chase that we did, but the heart of it was to identify the quotient of BPG by this ideal I with Z underline. And we sort of already knew that that we could construct a map like this and that it would be an equivalence on underlying spectra by this group action theorem we proved. And that lets us run an induction argument to check that it's an equivalence on geometric fixed points. And then the point was to say, well, actually we can check that both sides agree, that they have the same homotopy groups. And in particular, they're both sort of polynomial on a class in degree 2. And then the sort of work to actually check that this map was an isomorphism was to kind of give names to these classes. So to this class, which we called B here, and its powers. So we sort of gave them chromatic names in a sense, which I explained a bit in terms of these like slice differentials and thinking of these as kind of null homotopies of certain classes that show up in BPG. And I will say a little bit about that again later, but I also just want to mention about the slice theorem that, well, okay, yeah, this proof, as we saw, is pretty technical, and it's really the only proof that I'm aware of this theorem, and it's sort of, again, the heart of this paper, so it would be nice to know if there are other strategies to proving a theorem like this, and one strategy that HHR themselves point out in the paper would be sort of geometric argument. So I'm just going to say a geometric argument along the lines of Quillen. So let me elaborate on that a bit. I mean, if you think of Quillen's theorem on MU as saying something about, well, it gives a sort of modular description of the Whitehead filtration of MU. You could view it that way. And in that sense, this is sort of giving a equivariant version of that. And so Quillen has this alternative proof of this using these geometric Steenrod operations in his paper on elementary proofs, blah, blah, blah. And yeah, so that would be very interesting to see if something like that would work for these larger group cases. And this is something I've checked for the group C2, that you can also prove the slice theorem for C2, for MUR in this way, which is cool, but maybe not so interesting because the C2 case is kind of easy. So if it could be used to show these larger group cases, that would also be quite nice. Okay, so I just wanted to mention that just to also say, yeah, I mean, this was a really technical proof, but maybe there's a reason for it. Okay, now I want to get into finishing the proof. And well, let's just kind of take it from the beginning a bit. break this down in steps, kind of starting from the beginning of the story. So first we have this diagram that we drew a bunch of times. Let me give myself a little bit of space. We have this reduction map from the atom spectral sequence, from the Adams Novikov spectral sequence to the atom spectral sequence, and this Kervaire invariant problem by Browder's theorem was reduced to understanding the fate of the Hn squared classes in the atom spectral sequence. And we looked at all of the possible lifts of this class along this map. And we saw that they all had a very precise form. Using the Miller-Ravenel-Wilson computation of the two-line of the Adams-Novikov spectral sequence via the chromatic spectral sequence. And what we saw is that every lift of this Hn squared class was of the form, this particular beta class, plus classes that are sort of height less than or equal to 2. So they're all sort of in the ideal generated by 2v1 and v2. And with that in mind, we looked at this technique introduced by Ravenel to look at finite subgroups of the Morava stabilizer group. So this really comes from Ravenel's paper establishing the p greater than or equal to 5 case of this Kervaire problem, or sort of analog of this Kervaire problem. And we saw that it's sort of a straightforward calculation using these valuations that we cooked up in constructing this C8 subgroup of the Morava stabilizer group to show that any such lift here goes to something non-zero, which was sort of arranged by guaranteeing that the height was greater than 2 so that the junk went to 0, and then observing that this beta class sort of goes to more or less the sort of periodicity generator in H2 of this cyclic group cohomology. Okay, and then the sort of Hopkins-Miller / Gorse-Hopkins-Miller refinement of this diagram, sort of lifted this map through a map of spectral sequences converging to the homotopy of one of these higher real K theories. And this gave us our detection theorem. So we sort of could say enough about what this looks like to show that, in fact, now we know that if this class here survives, then it has to be detected in the homotopy of that higher real K theory via this map. Okay, so that's the basic setup that led us to look more closely at these higher real K theories, which leads us into the next step, which was this group action theorem. So I gave you guys a few different flavors of this. Let me do this. So the first one we talked about was just sort of the one you would start with when you're staring at this picture, which is to try to compute this E2 page. So that starts with determining this as a C8 module, and they prove something very general about these rings as modules over finite subgroups of the Morava stabilizer group, which specializes in this case to the statement that that this can be written as, well, a localization, or rather a completion of a localization, this would be C8, of a sort of normed polynomial ring where U generates a sign representation. U is a C2 equivariant class generating a sign representation. Okay, and then the sort of entry point for genuine equivariant homotopy theory was to try to sort of build a connective model that just picked out this polynomial part. And we did that. So that was to sort of build a sort of lowercase e4 that sort of maps to this one and just sees that part. And we did that, and that came via our other version of the group action theorem, which describes the homotopy groups of norms of MUR from C2 to these cyclic 2 groups as these sort of normed G polynomial algebras. So this was a suitable norm thing, and we have our BP version as well, which was the one that we actually wrote down the proof of. Okay, and this little E4 was defined as some suitable equivariant quotient of that. Okay, and then we sort of tie this part of the story, namely this part of the story, to this part of the story, the higher real K-theories part, via this theorem of Han-Shi. So they showed that there is a ring map, just a homotopy ring map of C8 spectra like this. Okay, and so one thing we could do is try to show that this map factors over the quotient through this connective model, which is true and can be shown. But one of the kind of nice tricks that HHR observed was that you could really get the same effect by asking for it to factor through a certain localization. And the sort of philosophy or kind of toy model of that I want to remind you guys of is that, I can, if I want to sort of take this sort of, universal thing and get something kind of finite height out of it, I can also just invert a height parameter. So if I do, Vn inverse mu, then that splits P locally as a sum of shifts of ENs, right? And so if I sort of content myself with like Johnson-Wilson theory looking things instead of truly connective models, this is an easier thing to do, and it's much easier to ask that a map factors over a localization than it is to ask that it factors over a quotient. Okay, so that's sort of why we end up actually just working with these, even though we could, in principle, go through this connective model point of view. Okay, and then step C was to put the slice filtration on MUG or BPG, which was just to say, okay, this thing looks like a big polynomial algebra. Let's filter it by the augmentation ideal of that polynomial algebra in a sort of equivariant way. And then we saw that this had a nice associated gradient in terms of this Bourdon homology instead of this more busy group cohomology. So to state it a little more explicitly, what we're getting from that is the slice theorem tells us, it tells us how to compute the E2 page of a spectral sequence converging to the homotopy of the G spectrum MUG. And that just comes from computing Bourdon homology of representation spheres. And we don't need to sort of get the full ROG graded homotopy of this, so we just looked at this positive cone region, which was all that we needed as input for these spectral sequences. And we saw this was really simple. It's sort of generated as an algebra by Euler and Thom classes, subject to some relations, namely the gold relations. Okay, and yeah, that turns out to be an extremely computable thing. Well, there it is. It's computed there, and that's our E2 page more or less. Our E2 page is kind of sums of this. Okay, so now we can sort of assemble the proof into three steps that I will now go through carefully. So what we do is we pick some class D, which I will explain through the course of the proof, and we consider the localization of MUC8 at this class D. And well, all that I want to say about D for now is that it's in a degree that is an integer multiple of the regular representation of C8. So that's what I mean by row 8.
Question, can I ask this previous one? Is that known for the circle group as well, or is it just for
I'm not sure. I'm not sure. Possibly.
The classes all come from.
Yeah. Yeah, that seems pretty plausible. Yeah. Yeah, I'm not sure. Okay, and what we will show is that this spectrum omega satisfies 3 properties. So first it has this gap property. Namely, it has this gap in its homotopy groups, in the homotopy groups of the genuine fixed points of it. And it has a periodicity, namely omega is equivalent to the 256 suspension of omega, C8, sorry, the fixed points. And the detection theorem says that if I take the unit of this theory that detects the Kervaire classes, then there is a factorization like that. Okay. Okay, and from this, the theorem follows that, hj squared doesn't survive when j is greater than or equal to 7, and which we now know is sharp, so this periodicity can't be improved. Okay. So that's kind of the overview of it. Now I'm going to go into the proof of these 3 pieces, which we've already done all the hard work for. Set myself up. Are there any questions on that overview? Okay, so let's start with this gap part. So this sort of, in the way that I state it and the way that I prove it, seems kind of harmless, like it's maybe the easiest part in some sense, but I think in a bigger picture, it's actually the hardest part. So if you think about like the descent spectral sequence for TMF, for example, the gap theorem is really the hardest thing to know about it, and you have to run the entire spectral sequence to get to it. And in this case, the sort of miracle of the slice filtration is that this gap is already visible on the E2 page. So namely, it holds for the associated graded, which is not the case for the homotopy fixed point spectral sequence. So that's really, all of these things need the slice filtration, but this is a huge upshot of it. Okay, and the gap theorem, as I said, just holds on the E2 page. So if I take some I in this range, then I can check from this positive cone thing that I wrote up there that the groups vanish in that region. That's not so hard to check. In particular, the same holds for the associated graded of this, and also then after I invert D. So because D is in degrees star rho G. Okay, that's.
Do you have a philosophical explanation for first vanishing, or is this a computation using cellular?
I mean, my feeling is it's so concrete that there's not much deep to say. It's just the way the representation spheres have a cell structure, which in turn is just the way you write the regular representation as a sum of 1- and 2-dimensional pieces, and it just pops out of that. I'll say some things later about sort of what Bredon homology is, or speculate on that a bit. But yeah, I think it's just really a concrete fact. Okay.
And you argue why this, when you have the positive cone and the negative cone,
yeah.
negative cones are spanned by this dualizing class, which just has a gap to 0.
Yes.
Having this dualizing property that has a geometric reason, right?
Yeah, that's right. Yeah, so like for C2, for example, you have this positive cone and then the negative cone, and the gap is exactly sort of the distance between them, and this can be phrased in terms of things like an Anderson self-duality of Z underline. Yeah, maybe that's another answer, yeah. Yeah, I think there are different ways of seeing why this gap should be there, yeah. Yeah.
So can you explain why this gives you a gap on the fixed points of omega instead of just on like the underlying? Like where do the fixed points come into the story?
So everything, the spectral sequence, like the filtration is a filtered G spectrum, right? So if I want to, so the point is, I guess now when I set star here to be 0, I have a spectral sequence converging to the pi I of the C8 spectrum I'm looking at. And if I do pi I of a G spectrum, where I is like an integer, trivial representation, this is the same thing as... Yeah.
So these pi's are...
G's are G, yeah, sorry.
Okay.
Yeah.
Okay.
Yep. Okay, so the periodicity part is a little bit more interesting, and it's sort of an elaboration on a really more basic version of this with KR, which I think a lot of things, that applies to a lot of things in this paper. But so let me sort of say what's going on there. So if I look at K theory, complex K theory, I have the twofold Bott periodicity of that, given by my class V1, and this lifts to an equivariant periodicity if I now move into ROG degrees for KR. So I have this lift V1 bar of this, and it gives me a periodicity like that. And the idea is that I can combine this periodicity with some Thom classes to get a periodicity on the fixed point spectrum. So let's just take as a fact given that this cohomology theory orients the representation for sigma, so I consider that as a vector bundle, and I'm saying it has a Thom class for that vector bundle, which is to say that I have this class U for sigma, which I'm just going to write it as like this because in the slice filtration is detected by the square of U2 sigma, so that same U2 sigma that showed up there. And this is in degree pi 4 minus 4 sigma. It's in degree 4 minus 4 sigma. And so the idea is I can combine these two things to get a periodicity on the homotopy fixed points of this. So how does that go? I just look at this class, U4 sigma V1 bar to the fourth, and which, just for coherence sake of what's to come, I'm going to rewrite like this. This has degree, 4 minus 4 sigma plus 4 plus 4 sigma. So rho is equal to 1 plus sigma, so that's where this 4 plus 4 sigma is coming from, and that's 8. So that's giving me 8-fold periodicity on the homotopy fixed points of Kr, which is Ko. Okay, and the reason this gives you a periodicity is, V1 bar is invertible, so that's fine. This U4 sigma a priori isn't, but it restricts to 1, right? These Thom classes restrict to the element 1 on the underline. So this is a unit as an endomorphism of the underlying spectrum, and so as a Borel G spectrum, it's a unit, and so I get this periodicity, so I get the sort of 8-fold periodicity of Ko from the 2-fold periodicity of Ku when I do this equivariant ROG periodicity thing. Okay, and that's sort of where our periodicity here is going to come from, and let me do something sort of in between the one appearing here and this one. So let's first look at Vn inverse BPR and show that this has some nice periodicities. Okay, so the idea is to look at the slice spectral sequence, where, as we proved last week, we have this family of differentials. Okay, So I have these differentials in the slice spectral sequence of BPR, and then I push them forward to differentials in the slice spectral sequence of this localization of BPR. And the point is now, once Vn is a unit, then I actually know that this power of A sigma is 0 on the next page. Okay, so then I can look at my next differential. And I have that this is, well, it's by the same formula. This is 0 because that power of A sigma was already 0 there. And this actually will tell us that this class here is a permanent cycle. So a priori, this just tells you, it's not a 2n plus 2 minus 1 cycle. But actually, in these slice filtrations, you sort of have a vanishing line, and the differential that does happen is always the one that goes to the vanishing line. So there are no there are no possibilities for longer differentials on these classes. So if this differential doesn't happen, then it is a permanent cycle. So it's a degree argument, but it, in any case, holds. Maybe I heard, yeah, so it's because Vn is a unit, so Vn is a unit and a permanent cycle. So I can divide by it here, and then it kills that. Yeah.
That's what you choose that or something.
Yeah. Okay, and so now I sort of do the same thing where I look at my Tom class and my periodicity class, and I sort of take the least common multiple of the powers that lands me in integer degrees, and I get a periodicity. So this has degree 2 to the n plus 1, 2 to the n minus 1, periodicity on, well, a priori, the homotopy fixed points of this localization of BPR. Again, using this Borel property. Okay, so that's nice. But we really don't want to have a statement about the homotopy fixed points because we want to work with the genuine fixed points where we have these gaps, for example. And so we need some mechanism to detect when this is the same as the genuine fixed points, and this is the condition of it being Borel. And that's going to follow in all of these cases from just a simple trick, which is the following. Let's say I have a ring spectrum whose geometric fixed points vanish for all non-trivial subgroups.
Sorry, Christian.
Yeah.
Why do we only get some homotopy fixed points?
Because it's not clear that this is a unit equivariantly. So all I know is it's some class. It's some class that survives.
It's not assuming it's ordered.
Yeah, that's right. Yeah. It's a subclass that survives, which restricts to 1. Yeah. Okay, so why are these things Borel? Let's suppose I have a ring spectrum whose geometric fixed points vanish at any non-trivial subgroup, and then let me take a module over this. This implies that M is Borel, and the argument is to look at the Tate square. So let's just look at M going into here. Okay, and so we want to show that this map is an equivalence. And so it would suffice to show that both of these things are 0. But the point is that this condition here tells you that E tilde G tensor R is 0, and these are both modules over that. So these are both 0. Okay, so that's a really easy way to guarantee that something's Borel. And so it holds in particular for this example because, well, the geometric fixed points of this class Vn bar is 0 for degree reasons, because the geometric fixed points of BPR is F2. Okay, so I inverted something which goes to 0 on the geometric fixed points, so the geometric fixed points of this thing vanishes. Okay. So now if I want to sort of imitate this argument, I need to produce some family of differentials in the slice spectral sequence for omega, for example. And that will come from the following theorem, which HHR called the slice differentials theorem. It says that in slice MUG, you have the following differentials. Let's write them down. On the powers of U2 sigma. Okay, and I'm going to name this class here FK. Okay, so these are differentials we have. This is the norm from C2 to G of TK. That's what that means. And well, this kind of is something I sort of alluded to in the proof of the slice theorem, which was that if we actually unravel the slice theorem proof, we sort of showed that actually these classes are null homotopies of something. And this is exactly the sense in which that's true. So you can write this as the following element. Like this. So this gives you some name for this class, and that's what I tried to say last week to conceptualize this proof a little bit, is we were really looking at these classes, you know, B and its powers, and trying to give some names to them, and that's sort of what we did, and then it results on the level of the spectral sequences in this family of differentials. Okay. Any questions while I raise? All right, so let's get into the proof of this. So I gave you a version of this already for the C2 case last week, and actually this is basically the same. So the idea is to, well, let's look at the part of the slice spectral sequence of this thing. I'm deducing something in slice MUG from slice BPG, you know, in the usual way of it being a sum of these things. It's just a little bit easier to see it here because of sparseness. So I want to just look at the V degrees of this form. So star is an integer, and this is the kind of degree that these classes U2 sigma and its powers are in. So if I want to deduce this, I only need to work in a region like this. And the basic idea of the proof is that, you know, they took their slice theorem and computed some slice spectral sequences in some small examples, and noticed that there was always a region of these slice spectral sequences that looked like a sheared version of the C2 spectral sequence. And so, sort of with that in mind, they looked at the following region, which is not hard to prove. What they write from this sort of positive cone calculation, but sort of looking at, deciding to look at this region is, kind of an insight that I think you really need to run some examples to see, but let me just state for now what it says. Okay, so if I look at degrees v of this form, and I look at degrees v comma s that satisfy this inequality, then the claim is that the slice E2 page consists precisely of this. Okay, and I mean, when I say that it's a sort of sheared version of the C2 spectral sequence, then that sort of is what I'm saying here. I mean, if you know what the slice E2 page for C2 looks like, it's exactly just this. Okay, and the upshot is that they could then run the same argument that we ran for C2. So namely, you run an induction argument that says, assume I have the differentials on these powers of U2 sigma through my k minus 1. And I can make a degree argument that says either this supports the claimed differential or none. So it's either supporting this differential or it's a permanent cycle. And that's the thing I said just in words before, that these differentials all sort of hit the vanishing line, so there are no longer possibilities for differentials on these classes. And then I can turn this claim into an argument about the geometric fixed points. So if I now invert a sigma, then I get a spectral sequence which looks like, well, I take my geometric fixed points of the associated graded, which is this, converging to the homotopy groups of the geometric fixed points of this, which is just F2. Okay, and then I unravel this. This is polynomial on U2 sigma over A sigma squared, F1, F2, and so on. Okay, so that's not so hard to figure out. I mean, we discussed last week what the geometric fixed points of the underline is, and then here you're taking a geometric fixed points of one of these normed polynomial algebras and using, if I norm something and then take geometric fixed points, there's a formula. Okay, and so now I am in the situation again where I have a spectral sequence where I know the E2 page and the E infinity page, and there's only one way for that to happen. Namely, I get the differentials of the claimed length on B2 to the k minus 1. Okay, so I must have these differentials in the localized spectral sequence. So by naturality, it couldn't have been the case that this was a permanent cycle. Otherwise, it would have went to a permanent cycle. Okay, so that's the argument. Yeah?
Why is it not to invert just A sigma to get the geometric fixed points?
I knew you were going to ask that question. I knew it. So yeah, you should invert A rho bar, right? But it turns out that like a power of A rho bar is A sigma or vice versa or something like that. Because the point is like A sigma is the Euler class coming from the index 2 subgroup. But the index 2 subgroup is being a subgroup of that is what it means to be a proper subgroup of G. So it's again the fact that the subgroup lattice is linear. Yeah. Or more concretely, if you take the infinite sign sphere, it's a model for E tilde P, as you can check directly. Yeah. Yeah, so that's a good point. And let's just record the following corollary. So I get, by the same argument I gave with Vn inverse BPR, I get that this product here is a permanent cycle. Okay, because again, we have the differential on one less power of this killing, A sigma times this, or a power of A sigma times this, and so the next differential will vanish when I multiply it by this, by the same sort of argument. Okay, so what we could do now is try and use this class as our as our sort of periodicity class like we did here. But that won't work because this isn't, I can't arrange by taking powers of this that this is in integer degrees, because here I just have a 2 sigma thing, and this is a norm of a class in degree rho, so it's a class in degree rho g times something. So it has all of these lambda representations in it. So I need to somehow force UVs into this product, which also account for those other representations, the lambda i's. Okay, so let's just now get to the proof of the theorem. So let me just say what our periodicity class is going to be. It's going to be the following. Squared to the 2 to the 4th. Okay, so I started writing this C8 superscript of this T1 because now I'm going to look at TIs that come from different subgroups. And if you remember the way we defined the TIs, they're not the same if I choose different subgroups. Like if I look at this, the TIs for C4, I have like mu tensor mu, and I'm taking a sort of automorphism there from the universal formal group to the one conjugated by the element of order 4. If I do this for C8, it's something different because I'm using the element of order C8 there. Okay, so these TIs depend on the group that you define them with, and I just want to record that. Anyway, this class has degree 256, and it's an improvement on this thing here because now I have a row bar here. So this is in integer degrees. Okay, and it's supposed to look like this. I mean, this formula sort of generalizes to this one. Okay, so then, okay, we could take this and say, well, let's just invert this now, and use that, because then we have our periodicity. But the problem is, this isn't yet a permanent cycle. So it doesn't sort of fall under the corollary here, because again, this isn't a U2 sigma, it's a U2 row bar. And so I have to somehow ensure that the other UVs in that product are permanent cycles first. And also, if I take the geometric fixed points of this class with respect to proper subgroups, I won't get something 0. And so this condition guaranteeing Borel won't work for us. So this is my periodicity class, but somewhat confusingly, it's not the D class. It's not the class I'm going to invert. Okay, so let me try to explain how we arrived there. So what do we know from this corollary? We know that this class is a permanent cycle in the slice of, well, I take mu h, and I invert the norm of tkh. Okay. So that class is a permanent cycle there because of this corollary. So this corollary applies to any group G. And if I invert the sort of this part, then I can divide by it, and I get that this is a permanent cycle. Okay, so that follows from the corollary. And then the way that I'm going to include other UVs into this product is to use the norm. And that satisfies the following formula. So this is just some formula that tells me what happens when I norm up Thom classes in Berdan homology. Okay, and it just follows from the usual kind of thing where if I norm up the representation sphere from H, I get the representation sphere for the induced representation. So that this formula follows from that. Not so hard to prove. Yeah. Oh, sorry, I didn't say. I have a sign representation for each subgroup of G. So this is an H equivariant class in the sigma H. So sigma H is the sign representation for H. Yeah. Yeah. Okay, the reason these are showing up is the following. So I want to look at this guy, because it's the thing appearing in this formula, and I'm going to express it, instead of it's not a U2 sigma, but it's a product of norms of U2 sigmas, which are permanent cycles. So that's what I'm going to use this for. So this is, I can write this using this formula as 4C8 U2 sigma 4 norm C2 C8 U2 sigma 2. Okay. All right. And then the idea is that I've expressed everything in terms of U2 sigma classes, albeit from proper subgroups. So I'm using like the order of the group as an abbreviation for the group. And the idea now is just that we want to say, well, if I norm up a permanent cycle, I get a permanent cycle. And then I can take this condition to get, sort of powers of this as permanent cycles. Okay, so let's just sort of inventory what this fact here gives us at subgroups of C8 for a moment. So I want to use, I want to go in a direction where I look at only height 4 classes. So I can sort of look at these TK classes for any k, but I just want to use height 4 classes because I'm going to need that for the detection theorem later. So I'm going to say more about that in a moment, but just for now, let me just say that we want height 4 classes. So if I look at this corollary, this tells me that this guy is permanent if I invert the norm from C2 of C8 of T1 C8. And T1 C8 is a height 4 class. In a sense, I'll explain later. Okay. If I look at now the C4 case, I get the following. Okay. So I have these height 4 classes I can norm up, and if I invert them, it will guarantee that these Tom classes are permanent cycles, and that therefore their norms will be permanent cycles. And then I can write this as a product of norms of these things. Okay, so how do I do that then? I have to take the sort of common power that's available to me in each of these, which is this 2 to the 4th. Okay. So then I look at that. And I want to guarantee that this is a permanent cycle. And what do I need to do to guarantee that? By what I have in this box over here, I need to let my class I invert be just the product of those 3 classes that I need to invert. So I can just write that like this. So that's going to be my class D. And let me write something here and then explain how this all fits together, because it's a little bit subtle. Okay, so what I want to say is that, first of all, once I invert these classes at each respective subgroup, I have that these things are permanent cycles. And then I want to know that the norms are permanent cycles. But to actually make that precise, I need to know that my slice spectral sequence has like a normed structure. And even for the localization, right? Because these classes are not permanent in the slice of MUG, only after I localize. So I need to know that I can do norms, but also after I localize. And to really do that properly, or at least in the cleanest way, I need some condition that guarantees that this localization is, again, a G-commutative monoid. And there's a condition for that, which is satisfied which is that the norm of this restriction of the class D always divides a power of D. So I can check that this always holds. This guarantees that that thing is a G-commutative ring, which guarantees that its slice spectral sequence has a norm structure. Okay, all this together guarantees that delta is a permanent cycle, because delta was just the product of this class and this thing, which was already a permanent cycle. Okay. And it also guarantees that it's invertible on the underline because, well, when I invert D, this is a factor of D, so it's inverted. And then this is invertible on the underline by the usual argument. It restricts to 1. So I'm done with the periodicity theorem if I can prove that this localization is Borel. So let me just say that, and then I will take our break. So the localization is Borel because, as before, the geometric fixed points of this class D is Borel because D consists of some factor which is always 0 on geometric fixed points at each subgroup. Basically, for the same argument that I made with Vn. So once I sort of take a class that comes from BPC4, for example, then its geometric fixed points has to be 0 if it's in positive degrees. With respect to geometric fixed points with respect to C4 has to be 0, because the geometric fixed points of BPC4 is HF2. So anyway, these classes are all 0, again, for degree reasons. And so when I multiply them all together, then I have that the geometric fixed points of this class is 0 at each proper subgroup, at each non-trivial subgroup. And this guarantees me Borel. Okay, I went a little over, so let me just pause, and then I'll say the detection theorem after, and then we'll be done with the proof and talk about some other things.